Alright, looks like we have a quorum of people. More than half are here, so I'm going to go ahead and get started. As you can see, my name is Brooks Henderson. I work here in Minneapolis, Minnesota with Staties. As you can see by the picture in the upper left, it is cold and snowy up here, though this winter has been much better than last winter. In fact, many people that like to do the ice fishing, like in that picture, haven't been able to do it very often until recently because we're getting above freezing half the days. So it's been pretty great from my standpoint. So I don't really do ice fishing. I like to get outside and walk and do some other fun things. So I've been enjoying the warmer winter here. But a lot of times you'll see people up on the lakes. This is a land of 10,000 lakes out there ice fishing. So we're going to talk today about Intro to Response Surface Methods. And actually this is part 2 of our webinar series on response surface methods. The first one focused more on what is response surface methods and started with a central composite design, a simpler design. This one's going to focus on the optimal, or sometimes known as custom designs. It's a very flexible design that will help you in some certain situations that we're going to go over today. By way of introduction, I did say my name is Brooks Henderson. My background, as you can see in the lower right there, is in materials science. And I actually recently got my CQE, so Certified Quality Engineer. Started out in metallurgical engineering, got my master's doing polymer matrix composites. Then I worked in the rubber industry at Caterpillar, where I first was saved by DOE. I was trying to implement a process and getting very low yields, but I was able to get it up to an acceptable yield level by using a DOE after many trials at not doing DOE and doing one factor at a time. So I see the power of DOE, and it can help you get to where you need to be. So with that, let's get started for today. We will be answering questions on the fly. Actually, I have my colleague Shari Kraber here to answer some of the questions that you guys have. So feel free to ask those as we go about the presentation, and she'll answer those. And here is our agenda for today. I'm going to start off with just an introduction to response surface designs, just a brief introduction to review where these designs fit in the realm of DOE. So that's where we're going to begin. And then we're going to have multiple examples. This is going to be a lot of show and tell on when you need to use optimal designs. For one case over there, you can see the picture. If you'd have a design with multiple linear constraints, which means perhaps you have to cut off the high level of your design space. You can't run, let's say, high temperature, high pressure. If you need to do that, as you can see over here in the picture, you may want to cut off a whole corner of that design space and only look in half of the design space. That's what we're going to talk about with the multiple linear constraints. Then we're going to also move on to designs with categoric or discrete factors, models other than full quadratic. So response surface designs, all the catalog designs are generally for quadratic models, but we can actually fit any model that we want with an optimal design. So it's very flexible, and we can put in whatever model we want. We will actually combine that one with an augmentation, which means adding runs to an existing design to fit a higher order model. So maybe you start with a quadratic, and that doesn't quite fit. You can actually go up to a cubic by adding some extra points, and the optimal design is what adds those extra points and chooses where to put them. So the key here is always choose a design that fits the problem. A lot of times we find people looking at a design out of a textbook or a catalog and saying, my experiment doesn't quite fit that, but I'll adjust it here and there, and oh, now I can fit it. But that's kind of like trying to pound a square peg into a round hole. We'd rather that you choose a design that fits the problem, and this design is very flexible and will fit almost any problem. So when you find that you can't quite fit your problem with the designs, this is probably the one you need to go to. Also, just want to point out, after the intro, this will be a lot of show and tell. I'll be going pretty quickly so we can go through all these 4 examples. So if you want to go more in depth into the analysis, definitely recommend taking a look at that Part 1 webinar for RSM that was presented by Shari Kraber a couple of months back. That's on our website and it was recorded, so you can go look at it whenever you have time. So let's first talk about where RSM fits in your strategy of experimentation. Most experiments or DOE cycles will start with a screening design. If you don't know anything about your process, great place to start is with screening. And what we're going to do in screening is try to narrow down all those possible factors. Perhaps you come up with a list of 15 or 20 factors that might affect the process and you don't know which ones are the most significant. Those would be known as your unknown factors. You want to screen those down and find the vital few that really do affect your process. And then you can go on to characterize the process, the second step, with something like a 2-factor interaction, factorial design, where you can actually fit those 2-factor interactions. That would be known as a Res 5. At that point, it's good to check for curvature. So here's our box for curvature. What you do there is you add some center points to see if perhaps you need to fit a quadratic model or if that 2FI will fit. If the 2FI will not fit and you do have curvature, so you'd say yes to this box, that is where response surface designs come in. So that's the sweet spot for RSM. If you have curvature in your system, you will go with that RSM design. And I will talk about a couple different RSM designs, and then we're going to focus on the optimal designs going forward. So one thing we like to point out with a response surface design is that you should only use it once you have narrowed down the number of factors, the ones that are really significant, and if possible, narrow down the range. You can look at, if you look at the entire region of operability, the whole area where, or factor space where your process will work, and you try to model that entire thing all at once, you're going to have a lot of absolutely nothing, as the sign points out there. And a lot of just these little waves all the way throughout. And trying to model all these little fine waves instead of just moving to the peak using RSM designs would take a lot more work than what we want you to do. So what the goal is to use factorial design to just find those linear models to push you up towards the peak and just kind of get up there near the peak. Then with RSM you can actually fit those peaks or valleys. So you start using a quadratic model here. As you can see, that's a parabola. You could fit a peak with just one parabola, a quadratic model. And that's what we want to do, is narrow down into that one peak and then use RSM. So some considerations you have when you're doing a response surface design is that it requires a quantitative response affected by continuous factors. It works best with only a handful of critical factors, as I was saying, and after you screen out all those factors that really aren't so significant, that's when you want to use RSM. We're going to produce an empirical model which will give you an approximation of that response surface, and you can fit, like I said, a peak or a valley with that quadratic model. If you have a couple of waves in the surface, you may need to have a cubic model, and so on and so forth. But we are hoping that you can narrow it down to a quadratic model, and that will be the simplest and most efficient thing to fit. You need more runs to fit those higher order models. And RSM is when you're really starting to try to optimize your factor settings. so we can actually go find that peak or valley and maximize or minimize the response. Here are some different classic RSM designs that we can choose from that are in your toolbox in Design Expert. The first one is a central composite design. There's actually a picture up here of that. And this is a classic 5-level design. It starts with the factorial design, which is represented by those blue dots and the cube. Are you hearing me at all? Because I can't hear me. I just realized that. So we start with that central composite design, and the nice thing about this, the reason it's called a composite design, is once that factorial design is run with center points, you can add these star points if needed to fit the curvature. So you start with the interior points there. The center points check if you have curvature. You do a little test to see if you need those star points or not. If you need them, then you add those. And it's a great design to fit a quadratic model. The next choice is also for a quadratic model. It's a box-Bankin design. Now that is actually only a 3-level design, which is kind of nice because you might not want to run all 5 levels. It's a little simpler for your experimentation. The other big difference is very similar in properties, statistical properties, to that central composite design. But the one big difference between the two is the box-Bankin design will not run those extreme cases, those corners of the cube, high, high, high level, or low, low, low level. So it kind of runs more of the centers of the edges and more interior points, not those extremes. And that could be useful in some cases. Also, it's only the 3-level design. So these are two great choices when you have a quadratic model and just a regular shaped design space that you can run your design in. The one we're focusing on today, that third one, is our optimal designs. So these are customizable for nearly any situation. You can use categoric factors along with numeric factors. You can constrain that design space, as I pointed out earlier, and you can add those constraints, which will cut off the corner design space. You can also use discrete factors. These are just the most flexible design, and when you can't fit those other two designs, this is where you're going to want to go. So this is a really useful design that we find everyone really likes to use, and it's very helpful. So that's what we're going to focus on today. So here is our 4 types of examples. And again, always choose a design that fits the problem. One of the best pieces of advice I've heard is always choose that design that fits the problem. If you find yourself modifying the problem to fit a certain design, then you're probably doing the wrong thing. So that's what we want to do here. If you can't use one of those normal designs, come to this optimal design and it will probably fit for your situation. So the first one we're going to focus on is where you may have to cut off that corner of the design space and a traditional design just won't fit. So here's a simple illustrative example on when you might need to use this. So we're going to talk about corn pudding. If you have never had corn pudding, you definitely need to try it. This is very good stuff. And my grandma actually makes really good corn pudding. What it is you got the corn casserole type thing, you've got some breading around it, and then the secret ingredient, gobs and gobs of butter. That makes it taste really good, so don't forget that part. But my grandma normally makes this for 90 minutes at 350 degrees Fahrenheit here, as you can see. Well, I always want to speed things up. I don't have time to cook that long, so normally I would cook it at 400 degrees for only 60 minutes. And I found that that works just fine. But if I go and leave it a little bit too long, it starts burning. So I do not want to go out here in this gray region or I get burnt corn pudding. Well, to try to optimize this process, perhaps I can go a little bit longer in time and make it maybe a little more moist. I've always heard that if you cook low and slow, it's a little bit better. So I wanted to test out these other possible points along the line between where my grandma cooks it and where I cook it. So there's the line that really defines what we can try. And once you've drawn this picture, it's pretty easy to put in constraints for this. But let's first ask the question, can I fit this design space to a standard CCD design, a central composite design? Will this work? So here's our central composite design for 2 factors. You've got the factorial points, those blue points around the edge, and then we have these star points right here. This is actually an FCD, a face-centered design, because we took those star points from the outside of the box and moved them into the edge. So that's known as an FCD, face-centered design, because we bring those points to the centers of the faces. Now that point right there, that fits in our yellow space, it'll work just fine. This factorial point will work fine. This other star point works fine. That one works fine. Even these center points are good. But what about if we get to this top star point? Is that going to work? Not really. That's going to be in my burnt region. That's at like 75 degrees and 400 degrees in 75 minutes. That's going to start burning my corn pudding. That will not work. This other star point also is not going to work. And this factorial point up here doesn't work. So the FCD will not work in this space, and that's where we need to go to that optimal design. Nice thing in Design Expert is we implemented a tool called Add a Constraint tool, and all you need to do, I'll simply tell you how this works. You'll have to go work on it yourself. I won't go through all the examples, but if you know where you want to avoid, and you can draw this picture, up in this upper right corner is the vertex that you cannot run, the furthest out point that you want to avoid. You type that in, A equals 90, B equals 400, and then you think from that point, what do I need to do to factor A to make this work? Well, I need to back it off all the way to 60 degrees or less. So that's my constraint point, and I put in A is less than 60. Then I also think, what do I need to do with B if I start at this vertex to make this work? And in this case, you go down, you back off B to 350 or less. So you just type in B is less than 350, and that will build you your constraint. So you click on this Add a Constraint tool right here, and then you will get this equation. So we just implemented that, I believe, in version 8, and it saves us from doing all the math or algebra to calculate this equation. You just put in the vertex and the limits, and then it will spit out this equation for you. You allow the design to be built, and this is what your design space is going to look like. This is just an example, so I'm just going to show you that quickly. We are avoiding all of this gray region, and our design points, those red points, were picked throughout this white region. That's our design space. Now, if we had the CCD design, we would have had a bunch of center points like up here in the middle. Instead, we split and kind of filled the design space much better, and then we also replicated some of the outside points, which actually gives us better precision of estimation on the outsides. Instead of putting all those center points in the middle, this is going to give us a little bit better precision in the outside of the design space. So you can see by the red dots, we've filled the design space very nicely with this optimal design. Now the optimal design, what this does is actually goes through different sets of points and places the points in different places to try to give us that good precision. And it will try out many different tries and sets of points and positions of points to try to give us this best case scenario. So let's actually move on from that simple illustrative example to a more real-world example. This is going to be on microwave digestion. If you're familiar with this, then you'll know what's going on here. I'm going to just give a quick summary. Don't have to worry too much about the science of it. Just look at the factors and the responses. But this is called inductively coupled plasma, ICP. And what we're going to do is put a sample with some solid particles into some acid in this container here. We're going to microwave it, and we're going to try to get all of that solids particles to be suspended and dissolved and ionized in that solution by heating it up in a microwave and using the right acid mix. So I'm just going to skip ahead. Don't worry too much about the science, to the responses and the factors.
Somebody's asking, is this an I-optimal design, D-optimal design, or something else?
Okay, there is a question about the optimality and how the points are chosen. As I build this design, I'll point out a little bit about that optimality and the different criteria. With our RSM designs, we usually start with an IV optimal design. So I'll point out that as we build this one. Someone was asking that. That was a good question. But here we're going to start with 3 responses. So we want to fully dissolve these solid solutions and then shoot them through this plasma. And our responses are going to be percent recovery of cadmium, chromium, and lead. So we want to fully dissolve them and recover all those solids. We're going to do this by adjusting the microwave heating times. There's 3 different heatings, 1, 2, and 3, and different amounts of time that we're going to try. There's also hydrochloric acid and nitric acid, and we're going to look at the ratio of those two as a response, or as a factor, and adjust that as well. So actually on this one we're going to start with a face-centered design and see how well that fits, or what might we run into in this case with using that face-centered design. So it's just like a CCD. We have the axial points, but we pull them in to the centers of the edges. And that's actually just under the CCD options. If you click options as you build that, you can click on face-centered, and it will pull those star points into the 1.0 region, or an alpha of 1 if you know what that is. That's just pulling it into the face of that cube. So that's what we did here. Typed in the factors and the responses, different times, different ratio of hydrochloric to nitric acid, and then here's our 3 responses. And what will happen if you build that FCD is the people that were running this went through their design. It's always a good idea, after you spit out a design, go through and mentally look at each run and see if it matches what you want to do and if it will all work for you. So what they found was they knew from experience that they wanted time 1 plus time 2 to be less than 30. And if you look at the FCD, there's some runs where that is definitely not the case. So we sorted by factor 1 and factor 3, which is time 1 and time 2. And then you see that we have some 10 and 10 runs, which only add up to 20. That is less than 30, and they know that that will not work just from experience. So that's where these constraints come from, is when you know from experience when something won't work, you can put in that constraint. So we want to get rid of these runs at the top. We also found, number 2 down here, that there's some cases where the T1 plus T2 is too big. It's greater than 50. So, for instance, this run number 2, we have a 30 and a 30. That's no good because that's 60. It's greater than our 50, so we want to actually do runs more up in between these 2 extremes. So we got to get rid of those runs. If you get rid of all those runs, you're not going to have a very good fit to your model. You may not even have enough points to fit the quadratic model. So instead of doing that and trying to cram this into an FCD, we're going to actually use that optimal design. So if you find yourself having problems and some of those runs won't work, that's where the optimal design will fit in. So we can actually just type in that constraint, 30 is less than A plus C, it's less than 50. It's because we wanted time 1 plus time 2 to be greater than 30, less than 50. So it's a pretty simple constraint in this case. You don't even need to use that constraints tool. You'll just type this right in Design Expert. So I'm going to show you actually how to build that. Right in Design Expert, let me do a actually open a design to save some time. This is very helpful if you guys ever find yourself wanting to rebuild a design. You just need to open the design that you're currently using. In this case, I'm going to use an optimal design. That's the digestion design. Now if I wanted to modify some of these levels and factors or change the design but keep all the same factors in there, this is a very helpful tip. Just do a File, New Design, and then say yes when asked to use previous design info. What that does is it puts all the factors and levels in that we had, and then we can just type right over them if we want to change something. So I'm just rebuilding this design I had already built to show you how it works. We're on the Response Surface tab, and we're clicking on an optimal design. We've got the 4 numeric factors. You can actually put however many factors you want in here. So we have the 4 factors, and you can put in your constraints right here. So type right in here what your constraints are going to be. And that was A plus C must be greater than 30 and less than 50. So that will ensure that we don't have any runs outside those bounds. And here's where the options are for what type of optimality this will be and some other things. The main thing that you want to look at right here is the option for what type of model this is. You can choose what type of model to fit. By default, we'll use quadratic unless you know something otherwise. Use quadratic model. This will allow you to fit a peak or a valley. If you think there's going to be an extra wave in there, you may need a cubic or a quartic model. But that will set, once you choose that quadratic model, it tells me that I need 15 model points to fit that. So it populates that box. And then we're also going to have 5 lack of fit and 5 replicate points. We add those in there. Those are a little bit extra points to check if that quadratic model is sufficient or not. It will give us what's called a lack of fit test. And it will compare whether our model fits as well as we expect it to fit, given the variation between those replicates. The optimality that someone was asking about before is right here. By default, we use IV optimality. What that does is minimizes the area under the FDS curve, basically. IV stands for integrated variance. And what it does is give us the best predictions possible. It focuses on giving us good, precise predictions. So the confidence interval around our predictions will be as small as possible. So we definitely recommend that for optimal designs. IV is actually also known as I or V, so that is the same thing. IV designs are same as I designs, same as V. They've been known as 3 different things. We chose IV. So you'll see in the papers sometimes I, sometimes V. We also have some other criteria on there that we won't go into, but for RSMs, stick with that default of IV. And that's the other tip. Whenever you're doing anything in Design Expert, the defaults are what we put in there because we recommend them. So don't do any changes unless you really know that you need to. So if you don't do any changes, you are doing our recommendations for the most efficient design and the best design that you can do. So just stick with the defaults and you're good to go. So that's all the options I'm going to go through. You continue, you can enter your responses. We got our 3 responses entered right there. You're still seeing everything, right?
I would answer questions.
My screen showing.
Yeah.
So here's the design, and if you looked really closely, you saw that it was iterating through 20 different iterations of moving these points around in a special algorithm to try to find the best integrated variance for that most precise design. And from all that moving and manipulation and algorithm, it picked out the best of the 20 tries and the best one that meets that IV criteria and gave us that design. So let's take a look at the design real quickly. On evaluation button right here, if you click on the graphs, you'll see the FDS curve, and that quantifies how precise your design is. We're trying to minimize the area under this curve when we pick those points. But let's go to the contour plot, and let's look at how those constraints were implemented, because that's the key in this example. The constraints were on time 1 and time 3. Time 3 is actually factor C, and we're looking at factor A on the x-axis, factor B on the y-axis. So we actually want to change the y-axis to be factor C. So I'm coming down here in the lower left, right-clicking on C, and changing that to the x2 axis. So now we're looking at A by C, and we can see those constraints. So right in here, we have a constraint, and right here another constraint, and we're only going to run in between those levels. So what was our constraint here? Well, we wanted A plus C to be 30 or more. So if you look right here, we've got A plus C is 10 plus 20, that's 30. We also have another one here where A is 20, and C is 10, so that's 30. They add up to 30 right along that line. Then if you go over here to another point, we've got A of 30 and C of 20. So that's another constraint that they add up to 50. We don't want to go above that, so all that is grayed out. And the last constraint point, again, is 30 and 20. So we're getting rid of all those areas that do not count in this design space that we don't want to run, because we know that digestion will not work. So that's what our constraints are doing for us. Now, we want to go back up to the design screen here. We've got the design. We can look at where the points are. We saw how they were put in there and how the region was constrained for us. And now, well, we've got all these empty boxes, right? We need to go out and actually run the experiments to get our data. Fortunately, in class and in a webinar like this, we have the data already. So we've created just a simulation that will put that data and plug it in for us. So I'm going to simulate the response here, and that's just something we created to dump the data right in there for me, so we don't have to type it in. So I'm going to pull up my simulation, and there we have the data. Presto, just like that. We got our experiments ran. We can analyze this data. So for each response over here, you're going to have a different node under the analysis node. So I'm going to click on the cadmium response, and I'll go through this analysis pretty quickly. Like I said, go back and review RSM Webinar 1 if you're not very familiar with this analysis. I'll just point out a couple things like the p-values that I look at and the quick things that I look through. I won't go into diagnostics very much in the interest of time. I'll try to finish this up within our hour to hour and a half that we scheduled it for. But you'll start, we don't need a transformation. You'll click from left to right on these buttons over to the fit summary. And this just summarizes the type of models we can fit. Notice that on this fourth line in the summary table it says cubic is aliased. Cubic is aliased. That just means we don't have enough data points to fit the cubic, which makes sense because we designed for a quadratic model. So in the summary table, it's the important statistics that get looked at, and then a design will be suggested. In this case, that quadratic design is suggested because it has a good p-value, low, a high lack of fit p-value, and I'll go into these a little bit more when we get to the ANOVA, and a good adjusted and predicted R-squared. So it suggests that. Click on the model, and that model is automatically populated here in the process order. All those terms with an M by them will be put in this model. And you can actually reduce that. I'm going to do that right away by clicking on the backward selection. Now that will take out any terms that have a p-value greater than this alpha out. And alpha out, in this case, we put at 0.1. So if I have any of those terms with higher p-values than 0.1, it will automatically take those out. And that will improve my model most likely. So I go left to right, click on the ANOVA button, and we have some terms at the top that were removed along with the p-values they had when they got removed. They're all greater than 0.1, so they took those out automatically, and we're left with this ANOVA table. We have A, B, C, D, and then some interactions and some quadratic terms in the model. All of those terms, if you look at the p-values, have low p-values. That's good. We have significant terms in that model. Less than 0.1 is what we chose there. A lot of people will go with less than 0.05 to be a little bit more strict. That's just a rule of thumb. It's quantifying your chances of being wrong saying these are significant. If I say 0.05, that means I have a 5% chance of being wrong saying that A, for instance, was significant. But you look at all those, we want low p-values. The model p-value combines all those together, and that should definitely be less than 0.05 or 0.1, whichever your cutoff is. And that's very low in this case. We have a very significant model. I told you about the lack of fit test. That's going to check whether or not this model fits well. Just kind of compares the variation that you see in replicates to what variation you have about the model. And the weird thing about this is you want insignificant lack of fit. So that p-value should be big. And instead of small, we're usually looking for really small p-values. This is the opposite. For lack of fit, we want to have a big p-value. And we do here. So it says not significant, which is good. I kind of think of it as when you're trying on clothes, do you want them to fit or not? Well, it says lack of fit, so we don't want that to be significant. That means my clothes don't fit or my model doesn't fit. But if we have not significant, lack of fit, then it does fit. So it's a double negative, kind of takes some getting used to. We want that p-value to be high. I also look at, scroll down here to the adjusted R-squared and predicted R-squared. That's a number between 0 and 1. Higher is better. It tells you how much of that variation in the data is being explained by your model. So the adjusted R-squared here is 0.93. We're explaining about 93% of that variation in the data. The big rule of thumb here is the adjusted and predicted R-squareds should be within 2/10 of each other. So in this case, they're about 0.05 difference. We want that difference to be less than 2/10. And also, as you can see right here, if you forget any of these rules, look at the blue writing. That will tell you what to look for. Predicted and adjusted R-squared are in good agreement. That means less than 0.2. So you can just read through the blue writing if you forget some of these things. And that software really is nice in that fact that it really guides you through the process. So those are good adjusted and predicted R-squareds. The precision should be greater than 4, and that is. So I'll go to the next button to the right. That's our diagnostics. In the interest of time, I'm not going to go through those, but safe to say I looked through all these. They are all good in this case. So we're going to skip ahead to the model graphs. Again, go to that previous webinar if you want the details of those diagnostics. But now that we've picked out a good model and we've verified it looking through the statistics and the diagnostics, we can predict the cadmium percent recovery on this graph based on all of our factors. So nice thing on this one, if you click on the 3D surface, you can see that you've got a nice peak here. And that's the good thing about a quadratic model. You can fit that rounded nice peak, and you can find the optimum right here at the top of the peak is around 97.5 or so for cadmium recovery. So that's what you do with the analysis here. Now we had two other responses that we want to optimize. We have chromium and lead. So what we have to do is go fit models to the chromium and lead responses, and then search the design space where we maximize all three of those things or target certain values. So let me go back to our slides here and see what else we can point out. Just on the model reduction, on the slides you will see a comparison of that full model to a reduced model down here. The full model means if I did not click on that backward selection and I didn't take out those insignificant terms, this is what we would have got. Our lack of fit would have been 0.3, but once we reduced it, the lack of fit value went up. That's good, to 0.39. And then this other slide right here is really telling the adjusted and predicted R-squareds. If you look at that full model before reduction, we had 0.583 for that predicted R-squared. So it's pretty low. The difference between adjusted and predicted is greater than our rule of thumb. So that's 0.4, not 0.2. So it's not good fitting model. So you wouldn't want to use that for prediction. But once you reduce and take out those insignificant terms, here's the reduced model scores. Those adjusted and predicted R-squareds match very well. So that kind of saves the day. If you find very low predicted R-squared, a lot of times it means you have to reduce the model. And we get the resulting contour plot, and then I've showed you the 3D plot. So I'm going to use that same method and go through the same numbers for the second and third response, cadmium and lead. Actually, just going to show you the results here and try to save some time. But the goal here is we're going to get to that optimization of these multiple responses. So we're going to go click on the second response, do the same set of steps there to fit a good model. Analyze each response separately, get a good model. Then we can optimize. That's the goal of an RSM design, to optimize, find the best factor settings to find that peak or valley and find the best trade-offs between the different responses. Got to have useful models in the optimization. So in order to get useful models, you must do design of experiments, and you must fit the models well. So here's some rules of thumb that you can look back at. You got to have a good p-value for that model. You have to have a high lack of fit p-value, and then adequate precision greater than 4. Another one that's not on here is that adjusted and predicted R-squared should match closely within 0.2. So if any of these don't happen for a certain response, that means you can't fit a good model of that response. That means you should leave it out of the optimization. Only optimize with something that you have a good model, because the optimization uses those models. If you had a bad model, it's going to drive you to a bad place. It might not be correct. So only use the responses where you got good models. And well-behaved residuals is that last thing. We didn't go through the diagnostics plots, but if you do, you want to make sure those are good as well. So we actually did that offline. I went through and I've got a file here with the analyzed responses. So I'm just going to pull that right up. And here we are. You can see right here under the analysis node we have the 3 different responses and they are all analyzed. So we went through that same process, we analyzed each of the responses, then they all turned out to be very good models. So what we can do then is go down here to numerical optimization. Click on numerical. You'll see the pattern here as you use Design Expert. We started by designing, evaluating, we went at the top here, then we went down to analysis, we did all those, then we went down to numerical. Just go top to bottom over here, and then left to right when you're into the button screens here. But here is our criteria for a numerical optimization. It's very easy to optimize your responses. Just click on the response. In this case it's cadmium. We want to pick, it would start at none here, but you pick your target, or you can either maximize it, you can minimize it, or you could target it. Or if you don't want a goal, you can say none. In range, we'll just keep it between the low and the high you put in. But here we're doing a target of 100. So 100% recovery is all we need to get to. That will be perfectly fine. We're leaving the lower and upper limits the way they were set. And those are just set by the lowest and highest results we saw in the data set. So just leave that in there. Then chromium, I'm targeting 100. Leave the low and high there as well. And for the lead response, I'm doing something a little bit different. The low and the high, you can see here on the graph, were 82.6 and 92.5. Those are the lowest and highest points we saw in the data set. But you can predict higher than that. The peak might come up a little bit higher than what you actually saw. So what we're going to do is use maximize, so it tries to push past that 92.5 all the way up to my upper limit of 100. Because ideally we want 100% recovery for all of these things. But what it's going to do is search through the design space, see how well we meet these goals, and give us a solution. So we'll see how far we can get. And you just click on the solutions button, and here we have some solutions. The first 4 columns for solution number 1 right here, that's what we're going to look at. The solution number 1 is does the best job of meeting my criteria. And it's telling me to put time 1 at 21.07, hydrogen to hydrochloric acid to nitric acid. H to N is a little hard to understand, but it's hydrochloric and nitric acid. The ratio should be 0.63. T2 is 25 and time 3 is 7. That should give us these results for our recoveries. So that's our best solution. We are able to get 100% chromium. We can only get that lead up to 92.3. We get the cadmium to 97.7. So that's the best settings right there for this process, and we would predict that we get these results. So from there, you'd set that experiment up and do a couple of confirmation runs to see if that's indeed what you get, to validate your model, and you're good to go. That would be the settings that you do if this does confirm and you get what you expect. So that's a good example of the optimization, and let's see what else we have to wrap this up. You'll get your results just like that, and that's all there is to it. That's using a design with multiple linear constraints. Just type those constraints in. You have to use the optimal design under the RSM tab to do this. So now we are going to move on to a design with discrete factors. If you have discrete factors, the only place you can do that is in the optimal design, RSM optimal. Be careful, there is an optimal design under the factorial tab. You definitely got to go to the RSM to do this. So we've got a stent in this case that we're going to try to coat with a spray. So you can see up in the upper left here, we're spraying the stent. Actually, what's going to happen is we just have the stent spinning on like a lathe, and then the spray nozzle is going to go back and forth across the stent and keep spraying continuously. What happens then is we have a certain flow rate is one of our factors that will determine how much of that spray we get on the stent, and then we have a number of passes. The key on the number of passes is you must do a full pass or you won't have an even coating. If you only did a half of a pass, you're only going to coat half that stent. So we must have an integer number of passes. 1, 2, 3. You can't have like 3.5. You just have those integer numbers. That's a discrete factor. And by the way, what we're coating this stent for, a stent is actually used in your blood vessels in an artery if you have a blockage. And it's like a little scaffolding. You fold that stent up, you put it in your artery, you pop it open, and that will hold your blood vessel open and get rid of that blockage. That's very helpful. Saves a lot of lives. People with heart attacks. You put in this stent. And one thing they want to avoid is getting clots on that stent, because this metal tends to draw clots. So what they're doing is spraying a drug on the stent. It's called a drug-eluting stent. And over time this drug is released and it keeps the blood from clotting in that area, that blockage again. So very nice stent here. We want to get a very even pass. So we have to do even coat. We have to do an integer number of passes. The other constraints, we do have constraints here. If you do a low flow rate with very few passes, you're going to get a very thin coating. It's not enough coating. So you have to do more passes at low flow rate. You also need, at a high flow rate, to do fewer passes, or you're going to get a huge coating. It's too thick. So I'll show you how to build this one in Design Expert. Again, I'm going to show you the trick where I want to just open my design because I've already built it. And this is called multiple linear constraints. Spray coating here. So I'm going to open that up. I'm going to rebuild the design, use previous info. You can see I chose optimal design on the response surface tab. 2 numeric factors, and the second factor, the passes, you just click on here and choose discrete, and you can put in 10 levels and you can type in all those 1, 2, 3, 4, 5, and it will only choose from these exact levels as it builds the design. The constraints we built right in there using the constraint tool. Since we're cutting off 2 different corners, we have 2 different constraints, you have 2 different equations in here. So here is our optimal design options. Again, we're going to do an IV optimal for a quadratic model. It will be a 16 run design, 6 to fit the quadratic with only 2 factors, and then 5 lack of fits and 5 replicates. Continue. Our only response here is the thickness of that coating. We want to optimize the thickness. This is a quick warning. Some of the points are outside of our design space, so it won't be able to choose from those. That's perfectly fine. Just hit OK. And it will go through and choose the best set of points to fit this design space. Again, we can look at the Evaluation tab and the graphs, and it will show our FBS graph. We don't have time to go through that, but click on the contour here, and you can see that we cut off the low corner, low flow rate and low passes. Got some gray down here. We also cut off the high corner. Then the red points right there, all those red dots are where we're going to run designs. If you see like in the center point here, there's a 3 by it. That means that there's 3 points right there at that point. So we are doing some replicates in the center of this design space. But that's the best set of points based on that algorithm to match our IV criteria. So it gives us the best, most precise predictions. Now I'm going to go down and analyze, click here to the design actual, and I need to actually type in my data or get my data from somewhere, run the experiments. So I'm going to right click on that response and just simulate this file again to save some time. We never have to run experiments in class. So here we are on the spray coating sim, populates my data, and I click on the thickness and I will go through the analysis here. Fit summary button, looks like the quadratic model will be the best. And this is actually a case where you, with the lack of fit, the extra points that we add, you could fit a cubic. It's not aliased. But that sequential p-value tells me the cubic terms aren't going to add anything significant, any extra explanation. So it suggests we just use that quadratic model. So clicking on the model button, it will populate quadratic. I can use reduction to get rid of those high p-value terms. And actually no terms got taken out this time, so it's the full quadratic model being fit. And we have for the model very low p-value, that's what we want to see. And all the terms are less than 0.1 p-value as well. So very significant model, significant terms. A lack of fit, high p-value, that's good. Insignificant lack of fit. Scrolling down, my adjusted and predicted R-squareds are very close, less than 0.2 difference. And that precision is greater than 4. So I'm going to go to diagnostics. Again, we're going to skip those. We've looked at them before. If you want more of the details, that RSM1 webinar, very good, by my colleague Shari Kraber here. That's fiercely typing answers to your questions. Keep them coming. She's getting tired. No, you're keeping her busy. Good job. So here is what we're going to get for our response surface. Again, we only have 2 factors to look at, so we don't have to worry about our factors tool changing to different things. We can look at flow rate and passes all at once. And I'm just going to point out some things on the contour plot here. Our goal for this design is to try to get a coating of 7 for that thickness. So let's actually put in a contour here at 7. And I see it is an hour right now. We've got a couple more examples that we'll be doing in the next 20 minutes or so. If you need to go, this will all be recorded so you can come back and look at this on the website. But I will continue on with those of you that are listening live. And let's put in a contour right at the thickness we want. Actually, the thickness is 9.5. I just looked at my notes. I want to fit a 9.5. So I'm going to right-click on this plot and add a contour. Oh, I almost hit it, 9.56. If I right-click on that box, I can set the contour value to whatever I want. I'm going to put 9.5. And what that contour means is anywhere along that line with those settings, I will hit a 9.5 thickness. So you can kind of just look at all these lines. If you go down and to the left, you get a 9 and then an 8, and you're getting less and less thickness. If you go up and to the right, more flow rate, more passes, you're getting higher thickness. It's also color-coded, so you can see right over here, there's our legend that shows the color coding. Low is going to be blue and high is red. Incidentally, a nice trick if you want to change that color coding scale, right click on this thing and you can change it to whatever makes sense to give you good colors. So there's that. But what we want to do here is just hit right there at 9.5 plus or minus a little bit. So you can see there's many different ways to do that. If you start at about 6 passes and a flow rate of 10, right here, that will hit 9.5. If you go for more of a flow rate, you decrease the number of passes, and then you can still hit it. So all the way along that line, we can find the goals here by just clicking on numerical optimization again. So I got a goal for thickness that I want to hit a target of 9.5. So I'm just going to put target and put in 9.5. And I want to actually hit that within plus or minus 0.45 was the specification. So I'm going to put in a 9.05 for the low, 9.95 for the high. So a lot of times you'll have a spec with a plus or minus value. You can just put in a target and then add and subtract to get the low and the high, and we'll see where we can hit that. Click on the solutions, and solution number 1 will give me a thickness of 9.5, so it's actually hitting right on. That's why you get a desirability of 1, because you met all your goals perfectly. Right on 9.5, with a flow rate of 18 and a number of passes of 5. So, one thing I'd like to point out here is the ramps view. This is much easier to look at to see where you're set for your factors and your levels. So look here at, let's see, the red dot here is halfway between 10 and 30. So we're maybe about 17 for the flow rate. The red dot for passes, number of passes, is about 5. Actually, it tells me what they are right down here. So 18 and 5. But it's just nice to look at the red dot to see how low and high you set your factors. And then, right here on the responses, it will be blue. So it's showing that peak. I'm trying to hit 9.5, and I hit right on 9.5. You can get results anywhere between the low and the high you set, so sometimes you may get off that peak. So I like to look at these, and then up at the top here it says solutions, and we have number 1 clicked. So I'm going to click on number 1. Then if I click on number 2, the red dots are moving around. So they moved a little bit here, but we're still hitting 9.5. If I click on 3, they're moving again, still hitting 9.5. So like I said, there's a lot of ways to hit 9.5. If I go way down the list to, like, let's say solution 33, am I still hitting? Still hitting exactly 9.5. Sometimes you might actually get a little bit off that peak, but all these solutions are hitting right where we want it. So I'm going to go back, click on solution number 1, and look at the graph and see where that is on our plot. If you look at the graph, it's showing my desirability. That's just the criteria we try to maximize to try to find our solutions, optimize all those goals. Click over here on the response, and we can actually look at thickness. And you'll see all these points. I'm looking at solution number 1. It actually flags it right there on our surface. If you click on number 2, that's a little bit higher on the flow rate and less on the number of passes. But let me see here. Actually, I'm going to look at the number of passes here. If you click back on the solutions, how many passes am I getting? Just clicking through here. Look at this one, number 7. I'm hitting the solutions, but I got 5.4 passes. Uh-oh. I said that I do not want to have those in-between passes. I'm not going to get the whole stent coated. So what you want to do to fix that is go back to your criteria, and you'll see a little pound sign whenever there's a discrete factor up here in this list. So I want to click on that passes, that discrete factor, click on restrict discrete factor. Then the solutions will all be those integer values. And now we're going to have way fewer solutions. I only got 7 solutions where I can hit that desirability or that goal. So that's what you need to do to restrict it. Sometimes you might, in this situation we have to hit those exact spots, but sometimes you only want to test in certain areas, but maybe you'll design something so that you can actually use a factor setting in between those levels that you use in the lab. So in the lab you might have different equipment, but then you might actually build an optimal equipment to fit the best settings. So that's very handy to use that restrict discrete. And then we only get 7 settings, and we're going to always hit right on a certain number of passes. All right. And this is just a slide we made pointing out the number of different solutions you can get that are seated right on this grid line of 2, 3, 4, 5, 6. You could even do 7 passes and hit within that plus or minus region that you wanted to hit. You won't be right on the target, but you're still going to be between about 9.05 and 9.95 in these 2 gray areas. So that's enough for that one. So that's a very nice way to use as discrete factors and optimize your system. So again, that's going to be with an RSM optimal design. That's what we're using all day today. The next example is if you have categoric factors along with those numeric factors. RSM optimal is where you need to go for that. And actually this is focusing on a catheter, which goes along with the stent example nicely, because this catheter you see in the upper left, it's like a little balloon that collapses inside the stent, and you blow this balloon up to expand the stent. So this actually delivers the stent to that region of the artery where you have a blockage. So you got to shrink it down, then blow it up to place the stent in there, then shrink the catheter back down and take it out of your body. The stent stays as like a scaffolding in your artery. So this example, what we have is 3 factors. We're going to extrude this polymer stent. So we're going to have a feed rate for the extruder. We have a zone 1 temperature, and the rub here is we have a raw material vendor. We can use for the raw pellets that go into the extruder either Acme or MCA. May sound familiar to some of you. 2 different suppliers of the raw material. That's a categoric factor. It doesn't have numbers and we can assign to it, and we can't do in between. So if you have that case with numeric and categoric factors, again pick the RSM optimal. Now you're going to put in 2 numerics and 1 categoric. I'll type those in, and I'm just going to, in the interest of time, I showed you the slide on how to build it. I'm just going to open it right up and show you that example. Actually, I'll point out the goal of this one as well. See if I have anything here. The response is the OD, the outer diameter of that catheter, actually has to mate up with the stent. So you have to control that outer diameter very well. And that's the response we're going to look at. We've got to get the right outer diameter. In this case, we're going to actually look at which vendor is going to meet that spec the best. It's kind of an interesting one. So this, I already have the data in there because I just opened up this file. So all I need to do is go through the analysis, and I'll do that quickly since we're getting close to the end here. It's going to recommend our quadratic model again. That's what we designed for. And I will backward reduce that. I often just go straight in there and reduce it and see what that does. It removed the a squared term, which had a pretty high p-value, so that makes sense. And that leaves us with a very significant model. All the p-values for the terms are significant, small. Lack of fit test says that our model fits pretty well. It's insignificant lack of fit. Adjusted and predicted R-squareds are matching, less than 0.2. So that's good, and good precision. skip over diagnostics and go right to the model graphs. And we want to hit a certain outer diameter, which is 2.45 plus or minus 0.05. So let's look at how we can do that. 2.45 plus or minus 0.05. So we can go to numeric optimization and try to do that. Click on OD and target 2.45. Now this is pretty tight spec. You can only go down to 2.4 and up to 2.5. If you click on the solutions, looks like we can hit it exactly. Our desirability is 1. If we look at the ramps, we hit that goal, that peak, 2.45. So search the design space, and it found some factor settings that gives us 2.45. I want to look at the graphs this time. The desirability will be greater than 0 when you can meet your goal. So anytime you see a color other than dark blue here, means we're meeting our goals. So solution number 1, we're able to meet the goals, but it's up there in the corner. Now looking at this factor tools, I'm going to drag out here, we're on the Acme vendor for that solution. We're able to hit the goal, so it doesn't really care how easy it is to hit that goal or how often we hit that goal. Our question was, do we want to use Acme or MCA? So what I'm going to do is look at this desirability and see how we're meeting the goals with each supplier. In fact, I'm going to introduce one other thing here. The graphical optimization is a perfect place to do this. If you go down to graphical optimization, it will carry over my lower and upper limits, and then I click on graphs. And it will show, just like the desirability, where we have this solution right up in the corner. Little wedge actually matches our goals. It's between 2.405 contour, or the 2.4 contour here, and then this other contour is 2.5. So it's just narrowing, highlighting what region actually matches those goals. And that's solution number 1. We're using the Acme vendor. If you look at the other vendor, click on down here on MCA, you see that huge yellow region? That's what we want to see. I could almost set my factor settings anywhere as long as I'm using MCA, and I will match my goals. So this one's a little tricky because the top solution isn't really the best one. If you actually look at the graphs and explore, you see that just clicking on MCA, the yellow region is where it actually works and it matches our goals, and it's way bigger with MCA than it would be with Acme. So I would choose MCA in this case to meet those specifications the best. Gives us wiggle room around in those settings. So MCA is the winner, not Acme. So unfortunately, Wile E. Coyote will continue failing to meet his goal of catching the Roadrunner because he always uses Acme. And if you look at the graphs here, you can see that the MCA is much flatter. That's why we meet the goals. If you look at the graph for Acme, it's going to be a big steep cliff. So when you have the choice, you want to use a flatter response surface, and that means it gives you some wiggle room if your factors drift a little bit. You'll have a more robust process. With that, we'll move on to the last example, which will demonstrate models other than full quadratic. We're going to start with a quadratic, and then if that doesn't fit, we will augment. I'll show you how to add a few runs to fit a higher order model. So this case is called vinyl solubility, and we started with this rotatable alpha on a central composite design. So let me point that out here. Central composite design is what we're going to try for temperature and stirring rate. So we didn't have any constraints or discrete factors or anything where we had to use the optimal design, so it's good to start with that central composite design whenever you can. Now this is a very good design for fitting a quadratic model. And it does have some extra points to test for the lack of fit. So we're going to try to lengthen the life of the concrete. This is a vinyl compound that must dissolve in water prior to the mixing. We're going to optimize that compound and mix it at a certain temperature and stir rate and try to get rid of that vinyl and make it dissolve. So that's the background here. Did a two-factor central composite design. And the standard central composite design, what we'll run into here, it's not enough to fit that cubic model. So if you ever end up trying to analyze it and you can't get a good model, you got significant lack of fit, you might need to augment your design. So let me open up that design and show you this. Open it up. Here's the original central composite design. Right here, it's a 13-run design for two factors. The response is solubility. If you click on the solubility to go analyze this, our fit summary is going to say quadratic model is the suggestion. Cubic is aliased. So we have to go with quadratic. Whenever it's aliased, you can't pick that model. So quadratic's the highest one we can pick. So I'm going to pick that, do a backward reduction. It actually eliminated some terms. We do have a significant model, but we have a big problem here. We have significant lack of fit. So the model is not fitting as well as we would expect looking at those replicates. Another big problem, if you look at the predicted R-squared, that is negative. That's horrible. That means you could actually just take the average of all your data points and use that to predict anywhere in your design space, and it would do better than this model. So the quadratic model is not sufficient. We don't get good results here. Some of the diagnostics might indicate this as well, but we don't have time for those. But let's look back at let me look at the model graphs first. 3D surface. If you see the 3D surface here, we've got a point here way off the surface of the space here. This pink point in the middle, it's not fitting our model. Our model is this colored surface. It's not fitting well at all. The center points are all below the surface. They should be being right around the surface, hovering up above it and below it. So we're not fitting well. If you look at the fit summary, there is a clue here that the cubic model might work. That sequential p-value, you want that to be low, and it is for the cubic model. The lack of fit for the cubic will probably be insignificant as well. So the extra degrees of freedom are used to look at that cubic model. Even though we can't fully fit it with the number of data points we have, we can look and see if it might work well. In this case, it will work well, it looks like. So what we want to do is go back to our design, and we can add a few runs to fit that model. So I'm going to go to Design Tools, Augment Design, and Augment. So that's all you got to do is make sure on this page, Design Tools, Augment Design, choose Augment. It's going to bring up the options for that optimal augmenter, just like the options on an optimal design. We want to click on the Model button now and actually change that from quadratic to cubic. So it added a few extra terms. These M's are going to be in the model. We got squared terms plus cubic terms now got added. So hit OK. It tells me it's going to add 6 model points for that. And I'll hit OK there. And it says, design has been augmented. Would you like to evaluate it? That's always a good thing, so we suggest you evaluate the design. I will go there by myself, but I'm going to click No real quick just to show you what augmenting is. Here's our 6 blank design points that we just added. So if we go out and run these, we will be able to fit the cubic model. To make sure we can fit the cubic model, that's what it was telling us to do. Click on Evaluation and look at the cubic model right here. It's got cubic. Click on the results. And it says no aliases found. That's the magic words you want to see for the cubic model. If it says that, you can fit the cubic model. So we're good to go there. all I need to do is run those experiments and put them in the results. So I'm going to simulate this response since we are in a webinar here. And this is the solubility. I'm going to put in the rest of the results, click on the analysis, and see if we can fit a good cubic model to this one. So now it doesn't say alias by cubic. It actually suggests that, and it looks like it's going to be really good adjusted and predicted R-squareds. So I can click on the model, can do a reduction, see if we can get rid of some of those high p-values. It did take two of them out there. You can see AB squared and A squared B. And we have a significant model and significant terms. Now the key here is the lack of fit is insignificant, so that means our model fits well. So adding those few terms, fitting a cubic model fits much better, and that predicted R-squared is now matching the adjusted R-squared. So that saved the day. And if we look at our cool looking response surface, these cubic models look kind of nice. Check this out. We have a little bit of a wave in there. And if you look at all the design points, they're all right near the surface. That's what insignificant lack of fit looks like. It's going to fit just as good as your variation in those replicates. So you can see there's not too much variation in those replicates, so the design points fit about that close to the surface. So just adding those few more runs, you need to use an optimal augment to do that and fit that cubic model. We're able to fit this data much better. And let's see here. If you look at that model again, here's a picture of it. You want to go to the red spots on the, to maximize our solubility, you want to go to these red points on the contour map, or the high points on that 3D plot. So that 3D plot is just showing your response floating on the z-axis, the up axis. So you want the high points. If you have that high temperature, looks like that will be the best solubility. You'll maximize it. It'll be high there. And stirring rate doesn't really matter if you're up there at that high solubility. You'll probably hit a pretty good, if you're at the high temperature, you're going to hit a good solubility, whatever stirring rate you want to use. So that's nice. And that is our final example. So I'll stick around with a few questions and answer some of them.
If you could go back and review the edit constraints button.
Okay, I will wrap it up here, and then I've got a few questions that we're going to answer, and you can keep them coming. I'll answer a few, and then we'll type answers. If we fail to get to your question, definitely email us at stathelp@staties.com. I'll show you that in a minute. But let me just summarize, and then we'll answer a few questions. For an RSM design, you have a few different choices. The top choices are a central composite design right here. If you can do like a full factorial and add a few star points, that's the central composite design. It's good for fitting a quadratic model. Box banking is a good alternative cubic or quadratic model fitter, and it's only 3 levels. It also does not go to the high or low. There's extremes. So that's the box banking. Those are good choices for a quadratic model. And then what we focused on today was the optimal design. That's your most flexible option. You can put in constraints. You can add categorics and discrete factors. You can do, like we just did, a cubic model or even higher. And this will be used to augment designs as well. So again, remember the golden rule, always choose a design that fits the problem. If you're trying to mend that problem to fit a certain design, you're probably doing the wrong thing. So give us a call or try out this design. We've got, let's see, just want to point out our website has a lot of good stuff on it, including a recording of this webinar and our previous RSM1 webinar. So definitely go in there and check that out. If you've got questions, just use this address right here. That's your key, stathelp studies.com. So if we don't get all your questions answered, there's a lot of people on the webinar today. If we don't get to them all, send it to stathelp@studies.com and we'll be sure to answer your questions. You can also call us at this number. Make sure if you're asking about statistics or DOE, ask for statistical help, and you'll get one of myself or the other consultants that will help you evaluate designs or look at your designs. But a lot of times it helps to email us the design files too, so we can help look through those. So thank you all for coming. Best of luck on your experimenting, and thanks for listening. I'll continue on the line a little bit longer here and answer a couple of questions. The first one was someone wanted to review the Edit Constraints button. So I will show you again how you can put those constraints in. Let me open up a file here. So I'll open up one of the files where we had constraints and just point that out. The easiest constraint we had was in the microwave digestion one again. So I lost my folder, so let me find that again. The microwave digestion had some constraints. So I'll review that, and that's an easy example of how you put in those constraints. For the more difficult constraints where you're trying to use that added constraints tool, you'll probably just need to give us a call or look for an example on our website. We have a lot of tutorials out there that will show you some of this stuff. But let me show you the quick one here. Again, I'm just going to modify this design or rebuild it. So I'll do a new design, say yes to previous info, and here's the Edit Constraints button. This one, our goal was T1 and T2. If you add those two times together, they must be between 30 and 50. So that's factor A and factor C here. So in the middle, we put A plus C. The middle has to have the factors only, and they could be factors with a number by them, like 4A plus 2C or something. But you must have the A's, B's, and C's in the middle. So A plus C is greater than 30, so the low limit of 30 and the high limit of 50. So when you add A and C together, they'll always be between 30 and 50. That's what that constraint's telling me. And then as it builds that, you can always check your constraints by going to the evaluation and then the graphs and click on the contour plot. Now we have multiple factors here. We have 4 factors and we can only look at 2 at a time. So this is a harder one to check than just the simple 2D we looked at. But we must have A and C on the graph to look at them. So I'm right clicking on C, putting that on the graph, and then you can see that we grade out anything where it adds up to less than 30. So here it's 20 and 10. Time 1 of 10, time 2 of 20, that's 30. And here it's, and add them together and it's 30. So we got to get rid of anything below that. Then the upper end, they add up to 50 at this point in the corner. Anything above that we got to get rid of. So that's the constraints there. Are there any other ones? And I don't think there's any other questions that haven't been answered by Shari. Or if we did miss you, definitely email us and we can answer that offline. But appreciate you guys all coming today. Be sure to visit our website and you can see the PDF of this presentation, and a recording will be up there in the next day or so. So you can tell your friends about it and learn more about the RSM. Thanks all for coming and have a good day.